So welcome back to Math 210, Calculus 1. So today's session is all about something called L'Hopital's rule. And this is material roughly corresponding to section 4.5 in the book. I've got a couple explainer videos on it that I hope you watched. But we'll go more in depth during this class and do a lot more examples. What this is a technique that we use to evaluate limits. And so you'll remember that earlier on in the course we talked about limits, and the reason we like limits is because the derivative of a function is a limit of difference quotients. So in calculus, we're very often interested in taking the limits of difference quotients, that is, taking the limit of like a ratio of one function to another one. And as we learned, we often get indeterminate forms, like we get something like if you want to take, like here are some limits that give me indeterminate forms. Like I could do limit as x goes to 1 of what? Like x squared plus 2x plus 1 over or I should say maybe limit as x goes to minus 1, x squared plus 2x plus 1 over x plus 1. And if you just tried to plug in, you would get 0 over 0. Nevertheless, we could do an algebraic calculation and basically factor this as x plus 1 squared and realize that the limit is actually equal to 0. But when you just try to plug in, you get an indeterminate form, like of the form 0 over 0. What are other ones? Like if I take the limit as x goes to 1 of I don't know. Let's look at natural log of x over x minus 1. The natural log of 1 is equal to 0 because x to the 0 is equal to 1. And of course, if I plug in 1 for x downstairs, I'll get 0. So this is another indeterminate form of the form 0 over 0. But in contrast to this one, I mean, this is a limit that you know how to do. Like if you see this on a test, what you'll do is you'll take limit as x goes to minus 1 of, you'll recognize the numerator as x plus 1 squared. And so you'll see that this is, I'll try to get out of the way of the camera. So you'll see that this is equal to x plus 1 is equal to 0. It's not really clear how to do this one down here. It's not really clear how to do this one. Like there's nothing you can really like factor there. And we've seen some things like if I take limit as x goes to 0 of sine x over x, this also gives rise to an indeterminate form 0 over 0. And we couldn't really calculate this any other way, but well, we could do like a graphical investigation. We could graph it and see that this was becoming equal to 1. And there was also an argument that I did online, like with one of my videos that I had you watch, where you can, like there's sort of a trick where you compare the areas of 3 triangles and use the squeeze theorem basically to show that this limit has to be equal to 1. But in other words, we used a special technique to work on this. And the question becomes, like, when you're trying to calculate a limit like this, for instance, that gives rise to an indeterminate form, is there a way, or like a uniform method, to also look at this and try to calculate the limit? Maybe it doesn't work all the time, but at least it works some of the times. And that's what this L'Hopital's rule is. Like, it says that if you take a limit as x goes to a of f of x over g of x, and if you get an indeterminate form like 0 over 0 or plus or minus infinity over plus or minus infinity, so this could be going to infinity, the denominator could be going to negative infinity, or you could have 0 over 0 like in this situation. So L'Hopital's rule says, like, if you have like the limit of a ratio of say differentiable functions, and let's say their derivatives are continuous, and if it's also true that you get an indeterminate form like this, then you'll be able to calculate that limit in the following way. So what you're interested in is like what is an indeterminate form really? Like, what does it mean when I say 0 over 0? I say the numerator is tending towards 0 and the denominator is tending towards 0. And when I'm trying to calculate the limit, what I'm really interested in is, like, how fast is natural log of x going to 0 compared to how fast is x minus 1 going to 0, like as x goes to 1. And what tells us how fast something is going to 0, like what tells us the rate of change, like that would be the derivative. So you might expect that if you're getting like 0 over 0, like you're in a situation like this, then one way to calculate this, you might guess, is to, instead of looking at the ratio of the original functions, you might look at the ratio of their derivatives. So you might, instead of investigating like how fast f of x goes to 0 versus g of x goes to 0, you might instead look at how fast the derivative goes to 0 compared to how fast the derivative of the other one goes to 0. And the amazing thing is that this equality turns out to be 100% true, at least under the hypothesis or like the assumptions that I mentioned. Of course, you need f and g to be differentiable. Of course, you need to be starting out with an indeterminate form, or else some technical things might not be true. This is actually hard to prove, so we're not really going to give you the proof. We're really just going to to take Math 312 or like real analysis for the proof. This course, this class is sort of like about stating the technique, giving like an intuitive explanation for why you might expect it to be true, like I've done, and then showing you how to use it. But just as a for example, let's look at this problem and then redo it using L'Hopital's rule. So in this example, I've got a equal to 1. I've got an indeterminate form of 0 over 0. And what I did was I rewrote it like this. I mean, you don't have to rewrite it to do L'Hopital's rule, but here what I did, my f of x plus 1 squared, my g of x plus 1. And, algebraically, you could make the cancellation, or using L'Hopital's rule, you could take the derivative of numerator divided by derivative of denominator. So let's try to use, I'll just try LH for L'Hopital. Let's just try to use that L'Hopital's rule. X goes to -1. And so what I'm going to get, so I could calculate 2x plus 2. Or if I wanted to use chain rule, it's 2 times x plus 1, giving me 2x plus 2. Like either way, it's the same thing. So 2x plus 2 upstairs, and then downstairs, the derivative of x plus 1 is just equal to 1. And the statement of L'Hopital's rule says, because I had an indeterminate form, the limit of this ratio is the same as the limit of that ratio. So the limit f over g is the same as the limit of their derivatives. But this one, there's no problem just plugging in. So I can just do direct substitution here to get 2 times negative 1 plus 2 equal to 0. So remember how I was saying that like if you're in the situation where you have an indeterminate form like this, then when you're trying to calculate that limit, what you're really asking yourself is, does x plus 1 squared go to 0 faster than x plus 1? And the answer is yes. Sort of goes to 0 faster by this extra factor of x plus 1. But how do you detect that? So one way algebraically to detect that is to do the cancellation. But the other way to detect that with L'Hopital's rule is, so what's going on? You know, you're seeing like the rate of change. So the two rate of changes of x plus 1, you know, basically got taken away because they were replaced with their slope. And what you were left with is this rate of change on top, which was, you know, going to 0 as it does. But this one was no longer going to 0 because it had been differentiated out. So that's kind of an explanation of, like, intuitively of why this works. You're going to 0 much faster up here, so this can withstand like two derivatives where you're going to 0 downstairs less fast when you sort of differentiate away that rate of change. So hopefully that gives you at least some intuition about why it works. It's also important to realize that if you don't have an indeterminate form, then this L'Hopital's rule might not work. So let's look at some examples where L'Hopital's rule might not work. So I'm just going to make some things up. So let's take x minus 2 times 4, and let's divide it by like x minus 2. And yeah, sure, you could cancel out the x minus 2's. I mean, I could, like, I don't know. You could cancel out the x minus 2's if you wanted to, but just sort of like for illustrative purposes. So my f is 4 times x minus 2. My g is x minus 2. I'm taking the limit as x goes to 1. So notice this is not indeterminate. This is not indeterminate because I could just plug in 1 and I'll get like 4 as my answer. There's no problem there. And if I take the derivative of the top and bottom, what am I going to get? So it looks like I'm just going to get 4 over 1. Limit as x goes to 1. So yeah, this one correctly calculates. The answer, but it was an indeterminate form. So you can get the correct answer when you have an indeterminate form, or when you don't have an indeterminate form. But on the other hand, you might not. Let's do another one. Let's see if we can cook something up. Let's take limit as x goes to 0 of like 1 over x. Let's do something like that. So this limit doesn't exist. if I put like a right-hand limit, then it'll be going to what, plus infinity? So it won't exist, but it'll be going to plus infinity. If I do L'Hopital's rule on this, what will happen? I take the derivative upstairs, I get 0, the derivative downstairs is equal to 1. Limit as x goes to 0 from the right of 0 is equal to 0. And this is giving me an incorrect answer. And in fact, this limit is plus infinity. 1 over x is tending towards infinity. It grows without bound as x goes to 0 from the right. But if I just try to compare the rates of change, then by taking a derivative, the derivative actually destroys the limit that I was trying to do. It just gives me 0. And so the reason why you have to assume that you actually have an indeterminate form is because like you need some balance here and there to ensure that like when you actually take that derivative, you'll you'll be left with something that you can actually properly compare to get the limit. But you can see how like it definitely doesn't work. Like if you have something that's not changing at all over something that is, you can't just replace that with 0 over 1 and expect to get the right answer. So L'Hopital's rule only works in the limited circumstances when you have an indeterminate form in the first place. But if you don't have an indeterminate form, if you can determine the limit already, then of course you don't need L'Hopital's rule. You can just do something else. So that's just something to watch out for. Like this one gave us the correct answer. This one gave us the correct answer, even though it wasn't indeterminate, like because of the fact that it was really the same thing on numerator and denominator. So when I differentiated that out, it didn't really affect anything. Just gave me the answer. The silliest example you could probably do is like, what if you took limit of 4 over 1 as x goes to 1, right? So that's definitely the number 4. It's constant, it's not changing. Have you tried to use L'Hopital's rule on this? You'd end up with 0 over 0 because derivative of a constant is equal to 0, derivative of a constant is equal to 0. So this is like if you tried to incorrectly apply L'Hopital's rule when you didn't have an indeterminate form, you actually go from something you can determine easily to something that's just sort of like nonsense. So just be careful on that front. Any questions or comments so far? Yeah, so let's solve this made-up problem then. So I want to use L'Hopital's rule to calculate this limit, and well, first I should verify that it's actually indeterminate form, which we've done. Natural log of 1 is 0, 1 minus 1 is 0. Let's check out what we get. Remember to keep on rewriting that limit, and now I take derivative of natural log, which is 1 over x. Excuse me. So this is why we have to remember to still be able to take, we have to remember to keep up our facility with calculating derivatives because we'll still need them. The derivative of x minus 1 is equal to 1. And so therefore the limit of as x goes to 1 of natural log of x over x minus 1 appears to just be equal to 1 because I plug in x equals 1 and get 1 over 1. And that's telling me intuitively that as x goes to 1, natural log and x minus 1 are approaching 0 at about the same linear rate. So it's telling me that the natural log of x appears to be behaving like a linear function, at least near x equals 1. I'd like to do a little bit of investigation, so let's actually investigate that with the software. So if I look at my f of x is natural log of x, and my g of x equals x minus 1. So you're looking at these two functions, and actually look at what's going on. You're just literally comparing this thing to its tangent line. So if you're comparing a function to its tangent line, of course that limit's going to be equal to 1, because as you zoom in, like the red function is going to be closer and closer to the tangent line, so the ratio is going to be equal to 1. But let's verify that anyway. So let's take natural log of x divided by x minus 1. That's the green function. And we're taking a limit near the point 1. And so, yeah, look at this. So red function, natural log, blue function, x minus 1. The green function is the thing we're trying to take the limit as x goes to 1. And you're seeing right here that even though it's not defined, of course, because it's indeterminate, you're seeing that's totally approaching 1, just like we thought. So L'Hopital's rule is helping us out. You know, basically L'Hopital's rule was differentiating the red part to make it look like the tangent line, and also differentiating the tangent line to make it go away, and so it left us with that single slope. So hopefully that helps try to like understand what's going on. Do some more problems. Let's do some more problems. Go ahead and erase the statement now. Let's take limit x goes to 0. This one's from the book, but I'll just write it down without looking at the answer too much. Sort of write it down. Let's try to do it together. So e to the x minus 1 over cosine x minus 1. So please calculate this limit as x goes to 0. You want to check that it's actually indeterminate. So when x is 0, you get e to the 0 equals 1 minus 1 equals 0. You get cosine 0 equals 1 minus 1 equals 0. So this really is a 0 over 0 indeterminate form, and we know we do have to check that. So let's use, like to make some little indication that I'm using L'Hopital's rule. So let's look at this. The derivative of e to the x is e to the x. The derivative of x is 1. The derivative of negative 1 is equal to 0. And then downstairs, derivative of cosine is negative sine. And derivative of negative 1 is, of course, 0. And so now you can say, okay, well, what L'Hopital's rule really tells you is that if this limit exists, then it's equal to that one. So this limit gave us an indeterminate form. What about this one? Plug in x equals 0 to get 1 minus 1 equals 0. Plug in x equals 0 to get 0. So this is still an indeterminate form. So L'Hopital's rule didn't do us dirty. It did its job. These two limits are equal to each other. The problem is, I guess excuse me, I guess it could be true that neither of them exist, or it could be true that the limit exists, but we still can't determine it in either case. Sorry, I'm coughing so much today, but it is definitely true that L'Hopital's rule isn't going to always work all the time. However, that doesn't mean that we necessarily want to give up immediately, because the cool thing here is, well, I've got an indeterminate form, so why not use L'Hopital's rule again? I've got an indeterminate form. Both these things are differentiable. If you think that applying L'Hopital's rule, again, might actually simplify something and not just take you in an infinite circle, then go ahead and try it. And here I'm hopeful because I have this constant that's going to disappear when I take another derivative. So let's see this. Let's take limit as x goes to 0, and here derivative of e to the x minus 1 is just e to the x, and the derivative of sine is cosine, so I'm going to get e to the x over cosine of x. And now here, I can plug in 0, and I can get e to the x equals 1, cosine 0 equals 1. So my answer is negative 1. So I just had to apply it twice. And let's see that on Desmos too. I mean, you can always try these, try these graphical explorations whenever you can, because I think they're also really, really nice. So I was looking at f of x equal to e to the x minus x minus 1. I was looking at, what's a pretty function? So I was looking at g to the x equals cosine x minus 1. There's like almost like a little symmetry there, isn't there? And I'm finally investigating like what's the ratio of the two of them. So I'm looking at f of x over g of x, and that's the red function. So you see what I'm doing? I'm graphing the numerator, I'm graphing the denominator. It's clear it's indeterminate because numerator and denominator are both going to 0. But it's also clear from the graph that the ratio clearly has a limit, and that limit's clearly going to negative 1. So this is a great way to check your work. Highly recommend it. Any questions or comments? More examples. The next one's also in my video, but it's worth doing again. So let's take limit as x goes to 0 of x times natural log of x, and this is an indeterminate form, but it's of the form 0 times infinity, right? Actually, it's of the form 0 times like negative infinity, but let's just call that 0 times infinity. Like maybe I'll call it like 0 times plus or minus infinity. Like, don't really care whether it's going to plus or minus. It's still indeterminate in that way. The problem is, like, you can't directly apply L'Hopital's rule to this, right? Because it's not in the form, it's not presenting itself to you as f over g. But whenever you have like 0 over infinity, you'll be able to rewrite this. Excuse me, whenever you have 0 times infinity, you'll be able to rewrite this in a manner so that it is f over g and does give you an indeterminate form. And there's two ways you can do it. Like, you can either say x times natural log of x is equal to natural log of x over 1 over x. Or you can say x times natural log of x is equal to x over 1 over natural log of x. Doesn't matter. Either way, like, allows you to rewrite this as a fraction. I like to write it in a way that's going to be easier for me to differentiate. So, like, it's easier to take the derivative of 1 over x than it is to take the derivative of 1 over natural log of x, at least to me, like, whatever. So I'm the one doing the example, so so I'll do it this way. So let's rewrite this as limit x goes to 0 of natural log of x over 1 over x. But of course, I challenge you, you can rewrite it that way too, and it'll work out. Now I've got an indeterminate form of the form plus or minus infinity divided by plus or minus infinity. And that is a valid form for L'Hopital's rule. If you did it this way, it would be 0 over 0, which is also a valid form for L'Hopital's rule. Doesn't really make a difference. So now I can try to use L'Hopital's rule and see if I get an answer. So the derivative of natural log of x is 1 over x. That's good so far. The derivative of 1 over x is minus 1 over x squared. So I can actually just, cancel a factor of 1 over x there. And give me 1 over minus 1 over x, giving me limit as x goes to 0 of minus x equal to 0. Which is telling me what? That appears to be telling me that x is going to 0 a lot faster than natural log of x is going to negative infinity. It's kind of surprising. Or to put it this way, 1 over x is heading towards infinity a lot faster than natural log of x is heading towards infinity, because the denominator is dominating the expression and sending it towards 0, even though the numerator is slowly trying to get to infinity. Let's try to verify our answer. We've got x times natural log of x. Maybe that's almost kind of looks like a Nike swoosh. Got x times natural log of x. We were taking the limit as x goes to 0. And you can see that's, it's going straight to 0. Let's check our rewriting of it. We had looked at f of x equal to natural log of x. We had looked at g of x equal to 1 over x. And we were taking limit as x goes to 0. And well, yeah, okay, so now here's what I'm talking about. Like f of x, the green function, is natural log, and that's escaping to negative infinity. And 1 over x, the purple function, is going to positive infinity. You're taking the ratio of the two, so you're saying, like, who's going to infinity faster, And it's not super clear just from looking at this picture, like, who's going to infinity faster? So now, like, it's starting to get clear. Like, it looks like, well, it certainly looks like natural log of x is getting closer to the asymptote quicker, which should tell you that it's going to infinity slower, right? Because you're not, dropping down quite as fast. So it's looking like this one's winning. It looks like this one's going to infinity faster, which should take the whole ratio to 0, which now let's look at. So h of x equal to f of, I don't know if you guys think this is interesting, but I think it's really interesting. And of course, we already knew that it was going to be the Nike check, but here's the ratio of the green one to the purple one. And so even though green one is going to negative infinity, it's doing it so slowly that the purple one is sending the entire ratio to 0. Any questions or comments? I want to kind of introduce you to all of the kind of grab bag of tricks that you'll see. Here's another example. Let's take limit as x goes to 0 from the right of one plus x to the 1 over x. So you actually can use L'Hopital's rule to try and do this. There's different ways to approach it. And first of all, again, like this is not presenting itself to you as f over g. It's not presenting itself to you like in a way that you can use L'Hopital's rule. When you try to plug in x equals 0, you'll get something like 1 to the 1 over 0. You'll get something that looks like 1 to the infinity, which is indeterminate. You can't determine the form of the limit from that. But it's not in a way that we can use L'Hopital's rule. And there's two ways that you can think about doing this. What I like to do here, like if you have a number that's bigger than 0, like x is going to 0 from the right, so this number is bigger than 0. If you have a number that's bigger than 0, then it's going to be equal to what? E to the natural log of a, right? E and natural log are inverse functions. So I can rewrite this as limit x goes to 0 of e to the natural log of 1 plus x to the 1 over x. That didn't change anything. But the reason for doing that is to try to get rid of the exponent, because like it's the exponent that's throwing me off. So I can use my exponent rules. It says natural log 1 plus x to the 1 over x. It's actually equal to e to the 1 over x times natural log 1 plus x, right? So basically I've got y equal to natural log of 1 plus x over x, and I'm looking at the limit. I'm looking at the limit now as x goes to 0 from the right of e to the y. And so what can I do? Like, how can I calculate this? Well, because of the fact that e to the y is continuous, like if this number y is approaching like a certain number as x goes to 0, then e to the y will approach like e to the corresponding number. So in other words, limit as x goes to 0 plus of e to the y is equal to e to the limit as x goes to 0 from the right of y, of natural log 1 plus x over x. Or to summarize, like once you're at this point, what you realize is that you really just need to take that limit and then plug it in. Just take that limit and then exponentiate it, and you'll have your answer. And this limit you can do. So this limit you can do with L'Hopital's rule, because As x goes to 0, you're going to have natural log of 1, which is equal to 0, and you're going to have x is 0, so you get 0 over 0 in determinate form. So it's sufficient to find this limit and then substitute that in to e to the y. Are there any questions on that process? Because that wasn't, I mean, I'll do it and I'll calculate the limit, but first I want to ask you if you have any questions on how I got to this point, because that's not nothing. Yeah, so let's settle this and try to figure it out. So the limit now is x. I'll rewrite the problem. Limit as x goes to 0 of natural log 1 plus x over x. So this thing I can use L'Hopital's rule on. I can take the derivative of natural log of 1 plus x, 1 over 1 plus x, divided by the derivative of x, which is equal to 1. And this, I can just plug in 0 straight away, so I can just write 1 over 1 plus 0 equal to 1. So this limit's equal to 1, and therefore, the limit as x goes to 0 of e to the y is going to be equal to e to the 1 equal to e. Telling me that limit as x goes to 0 plus of this quotient, of this expression, 1 plus x to the 1 over x. This actually limits to e. So any questions, comments on that? There's a connection to sequences that you may have seen that I'll go ahead and state since I can. So I'm taking like a limit as x goes to 0. If I make the substitution, x equals 1 over n, where n is like, usual natural numbers, 1, 2, 3, 4, 5. So x is like 1, 1/2, 1/3, 1/4, 1/5. Then x will be going to 0 from the right? And the answer that I get when I take the limit should still be e. I mean, I've got just sequence of numbers going to 0, plugging them in, and they'll tend towards e. But what happens when I rewrite this? So x going to 0 is like n going to infinity. So that's like limit as n goes to infinity instead of x goes to 0. And what's 1 plus x? That would be 1 plus 1 over n. And what's 1 over x? That would just be n. And that's telling me that this limit would have to be e. And this was actually the original definition. This is actually the original definition of E from back into the 1700s. That's how it was discovered. Like, people didn't know this limit in advance, but they knew it existed, and therefore they defined E to be the number that this sequence tended towards. And this came from a continuous compounding formula, like if you are going back to these like compound interest formulas, the compounding 12 months a year, you have principal times 1 plus like rate over n to the n times t. If you want to start compounding like not just 12 times or like 365 times a year, but compounding like an infinite number of times per year, you end up taking a limit. And then when you try to calculate what's your base, you end up with this formula and you get E. So this principal equals original amount times e to the RT is like a continuous compound interest formula comes from this stuff. So the number E actually came from finance. It didn't come from anywhere else. So just kind of interesting that it also pops up in so many other contexts. And certainly we see it in calculus a lot. I mean, there's more to the story for why this comes up in continuous compounding. But, so I'm intentionally not getting into all of that like right this second, because this isn't that lesson. But I wanted to at least point out that that's where the definition of E came from, and that it was related to interest. And that you can sort of, if you believe L'Hopital's rule, you can calculate this limit using that. So like if you wanted to reverse engineer all this, like someone gives you this limit without telling you the answer, how do you calculate it? You could actually go back and make this substitution and then try to calculate, this thing. And then use L'Hopital's rule and then get your answer and then finally like end up with this. So it's like in some sense, yeah, I'm just introducing L'Hopital's rule and showing you how to solve problems, but in another sense, we actually got to something pretty deep, pretty quickly, which was like how do you calculate that complicated limit, and the original definition of E. So for what it's worth, I think that's pretty cool. The last thing that I'll leave you with, so we've been looking at L'Hopital's rule as x goes to A. It also works with infinite limits. So if you're taking a limit as x goes to infinity or x goes to negative infinity, and you have f over g, same deal. If you get 0 over 0, if you get plus or minus infinity over plus or minus infinity, if f and g are differentiable, continuously differentiable functions, then L'Hopital's rule will still work. But it doesn't matter whether you're going to A or if you're going to infinity. If you have an indeterminate form with differentiable functions, it'll still work out for you. So you can use this to do things like if you wanted to take something like limit as x goes to infinity of natural log of x over x. So now you're interested in like what we call the asymptotic behavior. X is not going to 0, x is going to infinity, and you're comparing how fast these two things grow. So you definitely get infinity over infinity, natural log of x goes to infinity, x goes to infinity. The number one application you see from this, why do you care about problems like this? So again, say that you had x equal to n, you're just using natural numbers like 1, 2, 3, 4, 5. When you're analyzing computer algorithms, you'll see like you have an algorithm that runs in logarithmic time, like your input has length n, and then it takes natural log of n number of seconds to run, times a constant perhaps, or your input has length n, and the polynomial runs in just linear time n. And when you want to kind of like analyze the relative difference of two algorithms, you might well be looking at a limit of something like natural log of n over n, like for instance. So asymptotically, you're asking like how much better is this then that, or vice versa, or whatever. So you might actually want to be able to compute these limits. And so what you do is you instead move to calculus and take natural log of x over x and use L'Hopital's rule. I'd be getting a little bit too far afield there, but so that's some motivation. Like if you like computer science, there's a strong motivation for why you care about like doing problems like this, because they do come from analysis of algorithms. But for us, we're just sort of playing around in the sandbox of the abstract. We're writing down problems, we're trying to solve them. So how do you do this? We straightforwardly apply L'Hopital's rule. We take derivative natural log of x. It's 1 over x, derivative of x equal to 1. And we're taking, of course, the limit as x goes to infinity. And so 1 over x as x goes to infinity will limit towards 0. So this ratio is tending towards 0, which is telling you that x is tending towards infinity much faster than natural log of x, which is telling you that if you have an algorithm that runs in logarithmic time, that algorithm is way better than the algorithm that runs in linear time, because as the number of steps, as your input increases, this will take. So like what's the saying? Like as the input increases, as the number of steps increases, the extra amount of work that you have to do, like in this algorithm, would like completely overwhelm things, and that sends the ratio to 0. Okay, but just one more brief Desmos look. So we were looking at f of x equal to natural log of x, and we're looking at g of x equal to x, just like before. But this time, instead of going to 0, we're trying to look at the asymptotic behavior. We're going to infinity. So you can really see it, like just sort of like what I was saying. The x is going to infinity way faster than the natural log. And so if you look at this ratio, h equal to f of x over g of x, like what's that happening? The ratio is tending towards 0, because even though both of these functions are tending towards infinity, f of x or g of x equals x is going to infinity so much faster, and it's on the denominator there, that it's dragging down this ratio to 0. So your algorithm that runs in logarithmic time is much better than your algorithm that runs in linear time, because it requires far fewer steps as your input gets larger. So I was trying to say. Okay, so thank you everybody for your time and attention. Please email me any questions, or if you want to set up an appointment to talk, and we'll see you on Wednesday for our last day of class this week. Take care.
Thank you. Have a nice day.
You too.
Thank you.